So guys, in today's video we are going to study about electrophilic substitution reactions of ethers. So what is the major concept one has to understand over here is, of course we are going to treat aromatic ethers and we are going to study that how does your electrophile come and sit on those aromatic ethers. So before going to the depth of this concept, let me remind you, what do you mean by electrophile? Okay, this question is for you. Can you please answer me? What do you mean by electrophile? Yes. So electrophile in simple words, if I have to say, means they are the positively charged species. I repeat, electrophiles are the positively charged species. Okay. So now we are having an aromatic ethers and another reactant we are having as an electrophiles. Now the question arises, of course sir, we are reading substitution reaction. At which position, I repeat, at which positions whether your electrophile will come and sit will be the next question alva. ಯಾವುದೋ ಎರಡು ರಿಯಾಕ್ಟೆಂಟ್ ನ ತಗೊಂಡಿವಿ ನಾವು, ಒಂದು ಅರೋಮ್ಯಾಟಿಕ್ ಈಥರ್ಸ್ ನ ತಗೊಂತಾ ಇದೀವಿ, ಇನ್ನೊಂದಲ್ಲ ಏನ್ ಮಾಡ್ತಾ ಇದೀವಿ ನಾವು ಎಲೆಕ್ಟ್ರೋಫೈಲ್ ನ ತಗೊಂತಾ ಇದೀವಿ. ಈಗ ಪ್ರಾಡಕ್ಟ್ ಬರಬೇಕು, ಅಫ್ಕೋರ್ಸ್ ಈಗ ಪ್ರಾಡಕ್ಟ್ ಏನಾಗ್ತಾ ಉಂಟು, ಬರೋದು ಸಬ್ಸ್ಟಿಟ್ಯೂಷನ್ ಪ್ರಾಡಕ್ಟ್ ಆಗಿರುತ್ತೆ. ಹಾಗಾದ್ರೆ ಅರ್ಥ ಏನು, ನಮ್ಮ ಅರೋಮ್ಯಾಟಿಕ್ ಈಥರ್ಸಿನ ಯಾವುದೋ ಒಂದು ಪೊಸಿಷನ್ ಅಲ್ಲಿ ಈ ಎಲೆಕ್ಟ್ರೋಫೈಲ್ ಬಂದು ಕೂರ್ತಾ ಉಂಟು. ಆದ್ರೆ ನಮಗ್ ಗೊತ್ತು ಏನಂತ, ಯಾವತ್ತೇ ನಾವು ಅರೋಮ್ಯಾಟಿಕ್ ಸಿಸ್ಟಮ್ ಅಥವಾ ಬೆನ್ಝೀನ್ ಸಿಸ್ಟಮ್ ನ ಕನ್ಸಿಡರ್ ಮಾಡ್ತಿದೀವಿ ಅಂದಾಗ ಯಾವುದೋ ಒಂದು ಗ್ರೂಪ್ ಮೊದಲೇ ಇದ್ರೆ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದಟ್ ಗ್ರೂಪ್ಸ್ ವಿ ವಿಲ್ ಬಿ ಹ್ಯಾವಿಂಗ್ ಆರ್ಥೋ, ಮೆಟಾ ಅಂಡ್ ಪ್ಯಾರಾ ಪೊಸಿಷನ್ಸ್. ಇಸ್ ದಟ್ ಟ್ರೂ? So now the question arises, the incoming electrophile, I repeat, the incoming electrophile, whether they are going to sit in the ortho and the para position or in the meta position. Alva? ಬರ್ತಾರೆ ಎಲೆಕ್ಟ್ರೋಫೈಲ್ ಈಗ ಇಲ್ಲ ಅಂದ್ರೆ ಆರ್ಥೋ ಇಲ್ಲ ಪ್ಯಾರಾ ಪೊಸಿಷನ್ ಅಲ್ಲಿ ಕೂರ್ಬೇಕು, ಇಲ್ಲ ಅಂದ್ರೆ ಯಾವ ಪೊಸಿಷನ್ ಅಲ್ಲಿ ಕೂರ್ಬೇಕು, ಮೆಟಾ ಪೊಸಿಷನ್ ಅಲ್ಲಿ ಕೂರ್ಬೇಕು. ಕ್ಯಾನ್ ಯು ಪ್ಲೀಸ್ ಸೇ ಮಿ, ವಾಟ್ ಡೂ ಯು ಥಿಂಕ್, ವೇರ್ ಡಸ್ ದಿ ಇನ್ಕಮಿಂಗ್ ಎಲೆಕ್ಟ್ರೋಫೈಲ್ ಕಮ್ ಅಂಡ್ ಸಿಟ್? I repeat, where does you think the incoming electrophile will come and sit? Okay. So if you say that we want to see the resonance structures, well and good. So basically, we know what, whenever a hydroxy group was present on a benzene ring, for example, that of your phenol, of course we saw that it was an ortho and a para directing group. Why? Because this hydroxy group is an electron donating group, and we also studied about its resonance structures. Now the question arises that when we are talking about your aromatic ethers, what I would choose? Yes, the general way of representation of your aromatic ethers will be in this way, OR. So if I write in this way, the next question arises within us. What is that? Whether this group is an electron donating or an electron withdrawing. ಅಲ್ವಾ? ಅಫ್ಕೋರ್ಸ್ ಈಗ ಹೈಡ್ರಾಕ್ಸಿ ಗ್ರೂಪ್ ನಾವೇನಂತ ಹೇಳಿದ್ವಿ, ಎಲೆಕ್ಟ್ರಾನ್ ಡೊನೇಟಿಂಗ್ ಅಂತ ಹೇಳಿದ ಕಾರಣದಿಂದ ನಮ್ಗೆ ಏನ್ ಗೊತ್ತಾಯ್ತು, ಯಾವತ್ತೇ ಎಲೆಕ್ಟ್ರೋಫಿಲಿಕ್ ಸಬ್ಸ್ಟಿಟ್ಯೂಷನ್ ರಿಯಾಕ್ಷನ್ ಆದ್ರೂ ಕೂಡ ಇಲ್ಲ ಆರ್ಥೋ ಮತ್ತೆ ಪ್ಯಾರಾ ಪೊಸಿಷನ್ ಗೆ ಬಂದು ಕೂರ್ಬೇಕು ಎಲೆಕ್ಟ್ರೋಫೈಲ್ಸ್. ಈಗ ಕ್ವಶನ್ ಅರೈಸ್ ಆಗ್ತಾ ಇರೋದು ಈಥರ್ಸ್ ಅಲ್ಲಿ. ಸೊ ಇದನ್ನ ನಾವು ಯಾವ ತರ ಜಡ್ಜ್ ಮಾಡಬೇಕು? ಅಫ್ಕೋರ್ಸ್ ವಿ ಕ್ಯಾನ್ ಜಡ್ಜ್ ಓನ್ಲಿ ವೆನ್ ವಿ ನೋ ದಿ ಕಾನ್ಸೆಪ್ಟ್ ದಟ್ ವೆದರ್ ದಿಸ್ alkoxy group, alva, alkoxy group, whether it's an electron donating or an electron withdrawing group. Yes, very good, it is an electron donating group. Why? Nothing has been changed. OH na H na en madidini, replace madidini alkyl group inda, and we know that alkyls are also good electron donors. And of course on top of that, oxygen is also having the lone pair of electrons. ಇದು ಎಲೆಕ್ಟ್ರಾನ್ ಕೊಡುತ್ತೆ, ಇದು ಮೇಲೂ ಎಲೆಕ್ಟ್ರಾನ್ ಉಂಟು. ಅವಾಗ ಏನಾಯ್ತು, ಎಲೆಕ್ಟ್ರಾನ್ ರಿಪಲ್ಷನ್ ಆಯ್ತು, ಈಸಿಯಾಗಿ ಎಲೆಕ್ಟ್ರಾನ್ ಡೊನೇಟ್ ಆಗುತ್ತೆ. ಸೊ ನಾವು ವಾಟ್ ಯು ಕ್ಯಾನ್ ಜಡ್ಜ್? ಯಸ್, ಸೊ ನಾವು ದಿಸ್ electrons which are present on the oxygen atom will be given to that of your benzene ring. ಅಲ್ವಾ? ಸೊ ಅವಾಗ ಏನಾಯ್ತು, ಈ ಕಾರ್ಬನ್ ಆಟಮ್ ಮೇಲೆ ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಜಾಸ್ತಿ ಆಯ್ತು. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತೆ, ಈ ಎಲೆಕ್ಟ್ರಾನ್ ಈ ಕಾರ್ಬನ್ ಹತ್ರ ಮೂವ್ ಆಗುತ್ತೆ. So how can I write those structures? Please observe clearly. So now here you will be having a double bond character OR, and oxygen will be having a positive charge. So now this pi electrons has been withdrawn by this carbon, so this carbon will be having a negative charge. Yes or no? then of course here one bond as it is. Now what happens, now this electron density will lead to the formation of a pi bond, and this pi bond will be taken by this carbon. Yes. So how will you write? Remember, equal amount of positive and negative charges should be present whenever you are writing a resonance structures. So OR plus double bond. Here you will be having a negative sign. So now this will be coming over here. This will be coming over here. So now here you will be having as what? So now here you are having as a O R plus. Here you will be having a negative charge. Here one bond. Here one bond. Yes or no? Then of course now this would be given. This would be taken back. So you will be having the final structure will be in this way. OR. ಈಗ ಓ ಮೇಲೆ ಯಾವ ಪಾಸಿಟಿವ್ ಚಾರ್ಜ್ ಇರಲ್ಲ, ಯಾಕೆ ಈ ಎಲೆಕ್ಟ್ರಾನ್ ವಾಪಸ್ ಹೇಳ್ಕೊಂತು. ಅದೇ ಈ ನೆಗೆಟಿವ್ ಸೈನ್ ಎಲ್ಲಿಗಾಯ್ತು, ಪೈ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ ಫಾರ್ಮ್ ಆಯ್ತು. Here one bond, here one bond, here one bond. But the major thing now arises, electron density ಎಲ್ಲಿ ಜಾಸ್ತಿ ಉಂಟು. In simple words, in which positions can we find negative charges? Of course, here also we are finding the electron density is rich in ortho and para positions. Alva, ortho and para positions. So what you can say? Yes, alkoxy group, alva. Alkoxy group is an ortho-para directing group. I repeat, alkoxy group is an ortho-para directing group as that of your hydroxy group. So whether they will be called as a ring activators or a ring deactivators. Are you getting my question? ಯಾವತ್ತೇ ಆಗಲಿ ಎಲೆಕ್ಟ್ರಾನ್ ಡೊನೇಟಿಂಗ್ ಗ್ರೂಪ್ಸ್ ಇದ್ರೆ ಬೆನ್ಝೀನ್ ರಿಂಗ್ ಮೇಲೆ, ವೆದರ್ ದೇ ವಿಲ್ ಬಿ ಕಾಲ್ಡ್ ಆಸ್ ಅನ್ ರಿಂಗ್ ಆಕ್ಟಿವೇಟರ್ಸ್ ಅಂತ ಹೇಳ್ಬೋದಾ, ರಿಂಗ್ ಡಿಆಕ್ಟಿವೇಟರ್ಸ್ ಅಂತ ಹೇಳ್ಬೋದಾ? ಗುಡ್. ಸೊ ರಿಮೆಂಬರ್, whenever electron donating groups are present on the benzene ring, they are called as what? Ring activators. What they are called as? Ring activators. Yake? Because you can just see they are activating the ring. But whenever an electron withdrawing groups are present, what? Electron withdrawing groups are present. So what you can say? Ring deactivators. Ring deactivators. Alva. For example, your ring activators ge OH agirbodu, OCH3 agirbodu. They are all ring activators. Ring deactivators are now nodidivi nitration, electron withdrawing groups irbeku. Okay. So those groups iddaga enagutte, they will be called as what? Ring deactivators. But today we will be studying about what? Ring activators. So of course now from the resonance structures we came to know one important clue. What is that? Sir, if you are going to treat aromatic ethers with an electrophile, those electrophiles must and should occupy which position? Ortho and the para position. Mark my words, ortho and. I'm not saying or. What I'm saying and. So you are getting two products. So whenever an ethers, aromatic ethers are undergoing an electrophilic substitution reactions, you will be getting ortho and para products. Okay. So let us first start with the first electrophilic substitution reaction. Yes, halogenation. Basically, whatever now we are going to study about the electrophilic substitution reaction, we are taking a common aromatic ethers, that is your anisole. ಏನು anisole structure? Methoxybenzene. Alva, OCH3. So basically, when anisole is treated with your bromine, remember, in the presence of ethanoic acid, so what are the two products you are going to get? Yes, so one you are going to get as OCH3 at ortho positionally, one the bromine idre plus, please note my words, plus I am writing, hangare ಎರಡು ಪ್ರಾಡಕ್ಟ್ ಬರ ಸಾಧ್ಯತೆಗಳು ಉಂಟು. ಸೊ ಇಲ್ಲಿ OCH3, ಇಲ್ಲಿ ನಮಗೆ Br. Okay. So what you are going to get? One is you are going to get the orthobromoanisole and one more is a parabromoanisole. Alva, the ortho position. So orthobromo. ED structure again anta heltivi. ಎನಿಸೋಲ್ ಅಂತ ಹೇಳ್ತೀವಿ ಅಲ್ವಾ. C6H5OCH3 ಎನಿಸೋಲ್ ಅಂತ ಹೇಳ್ತೀವಿ. ಸೊ ಆರ್ಥೋಬ್ರೋಮೋ ಎನಿಸೋಲ್, parabromo anisole are the two important products. But one important thing we have to note over here. What is that, sir? Of course. So I will just to rewind your pages in your mind and go back to your haloarenes. Haloarenes ಅಲ್ಲಿ ನಾವು halogenation ಮಾಡಿದ್ವಿ ಅಲ್ವಾ. ಏನ್ ಮಾಡಿದ್ವಿ ಅಲ್ಲಿ, ನಾ ಏನ್ ಮಾಡಿದೆ ಅಲ್ಲಿ ಅಂದ್ರೆ ಕ್ಲೋರೋಬೆನ್ಸಿನ್ ನ ಕ್ಲೋರಿನ್ ಮಾಲಿಕ್ಯೂಲ್ ಜೊತೆ ಟ್ರೀಟ್ ಮಾಡೋತ್ತಿಗೆ ಇಷ್ಟು ಸಿಂಪಲ್ ಆಗಿ ನಾ ಮಾಡಲಿಲ್ಲ. ಇನ್ಸ್ಟೆಡ್ ವಾಟ್ ಡಿಡ್ ಐ ಡೂ, I have used over here as an halogen carrier catalyst alva. FeCl3 na add madidde. Rewind the pages in your brain alva. Go back to haloarenes. Alli halogenation na nodi on solpa. Imagine that you are having now chlorobenzene and you have to do its chlorination, that is halogenation reaction. The reaction was not so simple. What we have done, we have used over a halogen carrier catalyst, that is your FeCl3. Then only we have got the two products. What were they? Yes, ಒಂದು ಆರ್ಥೋ ಸಬ್ಸ್ಟಿಟ್ಯೂಟೆಡ್ ಕ್ಲೋರೋಬೆನ್ಸಿನ್, ಇನ್ನೊಂದು ಪ್ಯಾರಾ ಸಬ್ಸ್ಟಿಟ್ಯೂಟೆಡ್ ಕ್ಲೋರೋಬೆನ್ಸಿನ್. You can ask me, sir, why we want to study this reaction over here? Remember guys, so when we were talking about your halogens or a haloarenes, when they were undergoing a halogenation, remember, of course, there also we have mentioned what your chlorine is an electron donating. It is donating, that is the reason you are going to get products at the ortho and the para position. But meanwhile, you should also remember that halogens are electron negative. So this chlorine is also having the minus I effect. That means electron withdrawing. So ಆ ರೀಸನ್ ಇಂದ ಎಲ್ಲಾದ್ರೂ ಎಲೆಕ್ಟ್ರಾನ್ ವಿಡ್ರಾ ಆಗಿದ್ರೆ ಏನಾಗೋದು, ಅಫ್ಕೋರ್ಸ್ ನಮ್ಗೆ ಈ ಎರಡು ಪ್ರಾಡಕ್ಟ್ ಆಗ್ತಾ ಇರಲಿಲ್ಲ, ಹ್ಯಾಲೋಜಿನೇಷನ್ ಕೂಡ ಆಗ್ತಾ ಇರಲಿಲ್ಲ. ಆದ್ರೆ ನನಗೆ ಹ್ಯಾಲೋಜಿನೇಷನ್ ಮಾಡಲೇಬೇಕಿತ್ತು. ಮಾಡಲೇಬೇಕು ಅಂದ್ರೆ ಅರ್ಥ ಏನು, ಐ ಹ್ಯಾವ್ ಟು ಮೇಕ್ ಸಮ್ ವೇ possible that instead of this chlorine taking back electrons, it has to donate it. So ಆ ಒಂದು ಡ್ರಾಸ್ಟಿಕ್ ಕಂಡೀಷನ್ ಅಲ್ವಾ, ಫಿನಾಮಿನನ್ನ ಚೇಂಜ್ ಮಾಡ್ಬೇಕು ನಾನು. ಸೊ ಆ ಒಂದು ಡ್ರಾಸ್ಟಿಕ್ ಚೇಂಜ್ ನ ತಗೋಬರಕ್ಕೆ ನಾ ಏನ್ ಮಾಡಿದೆ, FeCl3 ನ ಆಡ್ ಮಾಡಿದ್ದು. It was only, you can observe, even in alcohols also we have done halogenation. There also I have mentioned that in the absence of halogen carrier catalyst ಅಲ್ವಾ, ಆಲ್ಕೋಹಾಲ್ ನ ಕೂಡ, ಫಿನಾಲ್ ನ ನಾವ್ ಯಾವಾಗ ಹ್ಯಾಲೋಜಿನೇಷನ್ ಮಾಡಿದ್ವಿ ಅಲ್ಲೂ ಕೂಡ ನಾವೇನ್ ನೋಡಿದ್ವಿ, in the absence of FeCl3 itself we have got the products. Why? Because remember, because both your phenol and that of your anisole, okay, whatever the groups which are present, they are what, ring activators. They have the tendency to donate the electrons itself. Taking back, there is no condition itself. ಸೊ ಏನೇ ಈ ಅನಿಸೋಲ್ ಅಲ್ಲಿ OCH3 ಅಥವಾ ಆಲ್ಕಾಕ್ಸಿ ಗ್ರೂಪ್ ಉಂಟು ಅಥವಾ ಏನೇ ಹೈಡ್ರಾಕ್ಸಿ ಗ್ರೂಪ್ ಉಂಟು, ದೇ ಆರ್ ಹ್ಯಾವಿಂಗ್ ಓನ್ಲಿ ಒನ್ ಫಿನಾಮಿನನ್, ದಟ್ ಇಸ್ electron donating tendency. But in a halogenation of your haloarenes, remember it is having two processes. One, it can give, another it can take. And moreover, the taking tendency, that is your minus I effect in haloarenes, is dominant. So that is the reason only in that of your halogenations of our haloarenes we have used a halogen carrier catalyst, that is your FeCl3. Able to understand? Okay. So we came to know that whenever anisole is undergone a halogenation, we are going to get an ortho and the para products in the absence of our halogen carrier catalyst. So this was one important electrophilic substitution reactions of our anisole or methoxybenzene. So guys, now next important reaction we are going to study is about your Friedel-Crafts alkylation. Do remember guys, whenever you are coming across the word or a name of the reaction as Friedel-Crafts alkylation, one reactant will be fixed. Which one is that? Yes, your methyl chloride. Methyl chloride, and remember Friedel-Crafts alkylation andaga methyl chloride irutte. Friedel-Crafts andaga anhydrous AlCl3 irlebeku. This is an important thing you should keep remember in your mind. ಯಾಕಂದ್ರೆ AlCl3 acts as a Lewis acid and it's an important catalyst which works in this reaction. Of course, the another reactant will be changing. ಅಲ್ವಾ, ಹ್ಯಾಲೋಅರೆನ್ಸ್ ಅಲ್ಲಿ ಏನ್ ಮಾಡಿದ್ವಿ ನಾವು, ವಿ ಹ್ಯಾವ್ ಟು ಕ್ಲೋರೋಬೆನ್ಸಿನ್. ಇಲ್ಲಿ ನಾವು ಈಥರ್ಸ್ ನ ಸ್ಟಡಿ ಮಾಡ್ತಿದೀವಿ. ಸೊ ಏನ್ ಮಾಡ್ಬೇಕು, ನಾವಿಲ್ಲಿ ಅನಿಸೋಲ್ ನ ಯೂಸ್ ಮಾಡ್ಕೊಂತೀವಿ, OCH3. You're getting my point? So whenever Friedel-Crafts alkylation comes, two important things will be fixed. One will be your methyl chloride in the presence of our anhydrous AlCl3. Next, it depends whether if you are studying the Friedel-Crafts alkylation in haloarenes, this reactant will be a chlorobenzene. If you are studying it in the ethers, this reactant will be an ethers. Is that clear? Okay. So now what you will be getting over here? Yes. So here we will be getting as OCH3. We will be having a CH3 as an electrophile we will be obtaining. One will be at the ortho, another will be in the para position. OCH3, here CH3. Alva. So what you can say, this is your 2-methoxytoluene. Alva, 2-methoxytoluene. This is our 4-methoxytoluene. 4-methoxytoluene. So ಇಲ್ಲಿ ಏನು ಮಾಡಿದೀವಿ ಅಂದ್ರೆ ಈ ಒಂದು ಕಾಂಪೌಂಡ್ ನಾವು ಪೇರೆಂಟ್ ಆಗಿ ಯೂಸ್ ಮಾಡ್ಕೊಂಡಿದೀವಿ. ಓಕೆ, C6H5CH3 is called as what? Toluene. ಅದಕ್ಕೆ ಈಗ ನಾವೇನ್ ಮಾಡ್ತಿದ್ವಿ, ಇದು ಈಗ ಸೆಕೆಂಡ್ ಪೊಸಿಷನ್ ಅಂತ. This will be first, this will be second. So 2-methoxytoluene. Toluene means this part, C6H5CH3. ಅದೇ ರೀತಿ ಈಗ ಇದು ಫಸ್ಟ್, ಸೆಕೆಂಡ್, ಥರ್ಡ್, ಫೋರ್ತ್. So 4-methoxytoluene. So what here we want to say? So whenever your anisole is treated with a chloromethane or a methyl chloride in the presence of an anhydrous AlCl3, aluminum trichloride, we will be getting 2-methoxytoluene and a 4-methoxytoluene. So this is another important electrophilic substitution reaction which is called as what? Friedel-Crafts alkylation. So Friedel-Crafts alkylation ಅನ್ಕೊಳ್ಳಿ ನಿಮ್ಮ ಮೈಂಡಿಗೆ ಬಂದ್ಬಿಡ್ಬೇಕು. ಎರಡು ಕಾಮನ್ ಆಗಿರುತ್ತೆ ಆಲ್ಕೈಲೇಷನ್ ಅಲ್ಲಿ, ಒಂದು ಮಿಥೈಲ್ ಕ್ಲೋರೈಡ್, ಇನ್ನೊಂದು anhydrous AlCl3. ನೆಕ್ಸ್ಟ್ ಯಾವುದು Friedel-Crafts? Yes, Friedel-Crafts acylation. Friedel-Crafts acylation. So here what you are going to do? So as we have seen, when it was a Friedel-Crafts alkylation, two things were important and they are fixed, that is methyl chloride and anhydrous AlCl3. So when you are checking for a Friedel-Crafts acylation, which one will be fixed? Yes, one will be your acetyl chloride, CH3COCl, and another as usual our anhydrous AlCl3. Of course, since we are reading this one in the concept of ethers, so you have to take one aromatic ethers. In this case, I am choosing my anisole, OCH3. So what is the product you are going to get? Very much important, the way of writing your substituent. See here, the C is linking with OCH3, alva. But when here ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಉಂಟು, ಇಲ್ಲಿ ಯಾವ ತರ ಸಿಗುತ್ತೆ ನಿಮಗೆ, I'll just show you. It is going to dissociate as CH3 C double bond O plus Cl minus. Why I am saying this? Because this carbon will be acting as an electrophile. Alva? Overall, this is overall molecule is an electrophile. Adre positive charge ಯಾವ ಕಾರ್ಬನ್ ಮೇಲೆ ಉಂಟು? ಈ ಕಾರ್ಬನ್ ಮೇಲೆ ಉಂಟು. ಸೊ ಈಗ ಯಾವ ಕಾರ್ಬನ್ ಹೋಗಿ ಫಿಕ್ಸ್ ಆಗಬೇಕು? ಇದೇ ಕಾರ್ಬನ್ ಹೋಗಿ ಫಿಕ್ಸ್ ಆಗಬೇಕೇ ವಿನಃ ಈ ಕಾರ್ಬನ್ ಅಲ್ಲ, ಈ ಆಕ್ಸಿಜನ್ ಅಲ್ಲ. So how will you write? Yes, so it will be having COCH3, very much important, the way of representation, plus one more you will be having as what? OCH3 ಇಲ್ಲಿ ಇರುತ್ತೆ, ಇಲ್ಲಿ ಕೂಡ COCH3. Why I am stressing it? Of course, I have said it before also. Some of you will write in such a way CH3CO ಅಂತ ಬರೀತೀರಾ. That is wrong. Why? Because you can only see this carbon is not having any positive charge. Instead, the carbonyl carbon is having the positive charge. So that should only go and link to our benzene ring. Getting my point? These are the silly mistakes we do whenever we are writing in a PU board exam, and that is the reason you'll be simply wasting your marks. So don't waste your marks in silly mistakes. Okay. So this is the mere representation of our, whenever your anisole is undergoing a Friedel-Crafts acylation. Very much important to mark these words: acylation, alkylation. In alkylation, your methyl chloride and anhydrous AlCl3 is common. In acylation, your acetyl chloride and anhydrous AlCl3 is common. Okay. So basically, let us first deal with its common name. So remember, here we are choosing now this one as the parent chain, and this is called as what? Acetophenone. C6H5COCH3. Ketonic group is there, Allah. So this is called as what? This only this part I am talking about. This part is called as what? Acetophenone. So now 1, 2. So 2-methoxyacetophenone, alva. This is 1, 2, 3, 4. This is called as what? 4-methoxyacetophenone. Okay. Why I am not writing its name? Because I want to give its IUPAC name also. Very much important for your competitive exam point of view. I want to give its IUPAC name, so I am not writing the common name. I'll just write it over here so that you will know its spellings. 2-methoxyacetophenone. Acetophenone. And this one is your 4-methoxyacetophenone. 4-methoxyacetophenone. Okay. Now let us deal with its IUPAC name. 1-2 methoxyphenyl. Methoxyphenyl. Next, what is there? I've just done 1, 2 methoxyphenyl. Okay, next this part, ethanone. Okay, ethanone, ethanone. So what I have written? 1-2 methoxyphenyl ethanone. Similarly, what will be its position now? Yes, 1 hyphen bracket 4. 1, 2, 3, 4. So methoxyphenyl, ethanone, methoxyphenyl ethanone. Are you getting my point? So this is the IUPAC name of this structures. Okay, somewhat it is unique, so that is the reason I just wanted to say its IUPAC name. So first they have treated which one? First they have written the positions 1, 2, alva 1, 2. So 1 anta bardidare. So 1 yake adu ethanone. Okay, you can, otherwise you can write it here also. So next is what? In the second position you are having methoxyphenyl. So they have first named the ether, methoxyphenyl. That is in the second position, and this is in the first position. So 1 ethanone, alva. 2 carbons, eth, single bond A, since functional group is ketone. So ethanone. Here also 1-4 methoxyphenyl ethanone. Are you getting my point? So this is about our Friedel-Crafts acylation. So till now we have read about 3 important electrophilic substitution reaction. That is, one was your halogenation, second was your Friedel-Crafts alkylation, and that of your Friedel-Crafts acylation. So next let us study about the next important and the last reaction, which is called as nitration. Nitration. Yes. So as we are knowing that we are studying an electrophilic substitution reaction. Alva. So whatever substitution should take place, that should be by an incoming electrophile. As I have mentioned earlier, nitration andre nitric acid common agi barutte nama mind ige. Hagadre nitration alli bari nitric acid tagondre NO2 plus generate agutta. My question is, in case you are doing a nitration and you are choosing only concentrated nitric acid, can you generate NO2 plus? Of course not. So what you have to use? Very good. Nitrating mixture. So in madbeku, we have to use what? Nitrating mixture. So nitrating mixture andre eno? It's a mixture of our concentrated sulfuric acid plus concentrated nitric acid. I have explained these reactions earlier also. Sulfuric, in this mixture what happens? Sulfuric will be acting as an acid, nitric will be acting as a base. One of my favorite reaction when I was in PUC. So even the mixture na tagondaga yen electrophile generate agutte namge NO2 plus. See, the plus charge is on the nitrogen. So that should only come and attach to our benzene ring. So what we will be writing? Yeah, very good. So first you have to choose our N-isol OCH3 plus 2HNO3 in the presence of, very good, concentrated H2SO4. Alva. So what you'll be getting, of course, incoming is an electrophile. One will be our OCH3 in the ortho positionally. See the part I am writing. The bonding is with respect to the nitrogen. Plus another part will be OCH3. Here comes our NO2. So what they are? Orthonitroanisole, paranitroanisole. In case if I want to write its IUPAC name, how can I write? I will be choosing this one as my parent. So nitrobenzene, 1-methoxy. Yeah, 1-methoxy hyphen 2 nitrobenzene. Okay, 1-methoxy 2-nitrobenzene, and this one will be what? 1-methoxy hyphen 4 nitrobenzene. Write it in one line itself. Sorry guys. 1-methoxy 4 nitrobenzene. Alva. So this is part I have written over here. So this one is 1-methoxy 2 nitrobenzene. This is one is 1-methoxy 4 nitrobenzene. Are you getting my point? So whenever our anisole is treated with a nitrating mixture, we are going to get an ortho and a para substituted products. One will be our 1-methoxy 2 nitrobenzene. Another will be 1-methoxy 4 nitrobenzene. Is that clear? Very much important. Now an important thing I have to discuss with you. Of course, we have learnt about electrophilic substitution reaction. And we came to know that whenever an electrophile is attacking our aromatic ethers, it is going to get substituting into two important positions. One is your ortho, another is your para. But my question is now, which one will be major, which one will be minor? That is, whether your ortho product will be major or whether your para product will be major. Are you understanding my question? Electrophilic substitution reaction ಮಾಡಿದಾಗ ಎರಡು ಪ್ರಾಡಕ್ಟ್ ಬರ್ತಾವೆ ನಮಗೆ, ಒಂದು ಆರ್ಥೋ ಒಂದು ಪ್ಯಾರಾ. ಈಗ ನನ್ನ ಕ್ವಶನ್ ಏನಂದ್ರೆ, ಆ ಆರ್ಥೋ ಮತ್ತೆ ಪ್ಯಾರಾದಲ್ಲಿ ಯಾವ ತುಂಬಾ ಮೇಜರ್, ಈಲ್ಡ್ ಯಾವುದಕ್ಕೆ ಜಾಸ್ತಿ ಬಂದಿರುತ್ತೆ? If you are saying para, I want the reason for that. Are you getting my point? If you are saying para, I want the reason for it. I'll give you 3 seconds. Okay. So remember, whenever we are doing an electrophilic substitution reactions, our para product is the major product. Para is the major product. Para isomer I have to add. Para isomer is the major product. What is the reason, sir? Okay, let us deal with it. I can give a clear explanation by taking this one as an example. Remember guys, here also your alkoxy group ಏನಾಗಿರುತ್ತೆ, ಬಲ್ಕಿ ಗ್ರೂಪ್. ಆರ್ಥೋ ಪೊಸಿಷನ್ ಅಲ್ಲಿ ನೋಡಿ, ಇದು ಕೂಡ ಏನಾಗಿದೆ, ಬಲ್ಕಿ ಗ್ರೂಪ್. ಸೊ ಅವಾಗ ಏನಾಗುತ್ತೆ, ಈಗ ನೀವು ತಿಳ್ಕೊಳ್ಳಿ, ಇಫ್ ದೇರ್ ಇಸ್ ಓನ್ಲಿ ದಿಸ್ ಮಚ್ ಸ್ಪೇಸ್ ಇಸ್ ದೇ, ಓಕೆ, ದಿಸ್ ಮಚ್ ಸ್ಪೇಸ್ ಇಸ್ ದೇ, 2 fat fellows are coming side by side, okay, no place at all. Okay, so what they will do, of course they will try to push each other ಅಲ್ವಾ. ಇವೆರಡು ಏನ್ ಮಾಡುತ್ತೆ, ಒಂದಕ್ಕೊಂದಕ್ಕೆ ಪುಷ್ ಮಾಡಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಮಾಡುತ್ತೆ. ಅವಾಗ ಏನಾಯ್ತು, ಸ್ಟೆಬಿಲಿಟಿ ಕಡಿಮೆ ಆಗ್ತಾ ಉಂಟು ಅಲ್ವಾ. ಇದು ತುಂಬಾ ಎನರ್ಜಿ ಕೊಡ್ತಾ ಉಂಟು, ಇದು ತುಂಬಾ ಎನರ್ಜಿ, ನಂಗೆ ಸಾಕೆ ಆಗ್ತಲ್ಲ ಜಾಗದಲ್ಲಿ ಇರಕ್ಕೆ. ಸೊ ಒತ್ತಡದಲ್ಲ ನಂಗೆ ಕೂರ್ಬೇಕು. ಸೊ ಅದಕ್ಕೆ ನಾ ಏನ್ ಮಾಡ್ತೀನಿ, ಆ ಪೊಸಿಷನ್ ಇಂದ ಸ್ವಲ್ಪ ದೂರ ಹೋಗಕ್ ಟ್ರೈ ಮಾಡ್ತೀನಿ. ದೂರ ಹೋದಾಗ ನಾ ಎಲ್ಲಿಗೆ ಬಂದೆ, ಪ್ಯಾರಾ ಪೊಸಿಷನ್ಗೆ ಬಂದೆ. ಸೊ ಇಲ್ಲಿಗೆ ಬಂದಾಗ ನಂಗೆ ಏನಾಯ್ತು, ನನ್ನ ಮಧ್ಯದಲ್ಲಿ ಯಾವ ತರದ್ದು ಒಂದು ಫೋರ್ಸ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗ್ತಾ ಇಲ್ಲ, ರಿಪಲ್ಷನ್ ಫೋರ್ಸೇ ಇಲ್ಲ, ಸ್ಟಿರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಕಮ್ಮಿ ಆಯ್ತು. ಸೊ ಸ್ಟಿರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಕಮ್ಮಿ ಆಯ್ತು ಅಂದ್ರೆ ಅರ್ಥ ಏನು, ಎನರ್ಜಿ ಕಮ್ಮಿ ಆಯ್ತು. ಎನರ್ಜಿ ಕಮ್ಮಿ ಆಯ್ತು ಅಂದ್ರೆ ಸ್ಟೆಬಿಲಿಟಿಗೆ ಯಾವ ತರ ರಿಲೇಷನ್, ಎನರ್ಜಿ ಇಸ್ ಇನ್ವರ್ಸ್ಲಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ಸ್ಟೆಬಿಲಿಟಿ. ಎನರ್ಜಿ ಕಮ್ಮಿ ಆಯ್ತು ಅಂದ್ರೆ ಸ್ಟೆಬಿಲಿಟಿ ಜಾಸ್ತಿ ಆಯ್ತು. ಸೊ ನಾನು ಹೇಳಿದ್ದೀನಿ, ರಿಯಾಕ್ಷನ್ ಯಾವತ್ತೇ ಆಗಲಿ ಸ್ಟೇಬಲ್ ಕಂಡೀಷನ್ ಹೋಗಕ್ಕೆ ಟ್ರೈ ಮಾಡುತ್ತೆ. ಸೊ ಆ ರೀಸನ್ ಇಂದ ಆರ್ಥೋಕ್ಕಿಂತ ಪ್ಯಾರಾದಲ್ಲಿ ಸ್ಟಿರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಕಮ್ಮಿ ಇರೋ ಕಾರಣದಿಂದ always remember our para products will be the major and ortho products will be the minor. Note this word. Okay, not only in this case, you can take in nitration also. Nitrogen ಮೇಲೆ ಕೂಡ lone pair of electrons ಇರುತ್ತೆ. ಇದು ಕೂಡ ಏನು ಬಲ್ಕಿ ಗ್ರೂಪ್, ಎಲೆಕ್ಟ್ರಾನ್ ಡೆನ್ಸಿಟಿ ಏನಾಗುತ್ತೆ, ಏನೇ ಆಗಲಿ ರಿಪಲ್ಷನ್ ಇದ್ದೇ ಇರುತ್ತೆ. ಸೊ ಏನ್ ಮಾಡುತ್ತೆ, ಆದಷ್ಟು ದೂರ ಬರೋಣ ಅಂತ ಇಷ್ಟಪಡುತ್ತೆ. ಸೊ it will come at the paras. In all these cases, our para is the major. ಹ್ಯಾಲೋಜಿನೇಷನ್ ಅಲ್ಲಿ ಆಗಿರ್ಬೋದು, ಫೀಡಲ್ ಕ್ರಾಫ್ಟ್ಸ್ ಆಲ್ಕೈಲೇಷನ್ ಅಲ್ಲಿ ಆಗಿರ್ಬೋದು, ಫಿಡಲ್ ಕ್ರಾಫ್ಟ್ಸ್ ಅಸೈಲೇಷನ್ ಅಲ್ಲಿ ಆಗಿರ್ಬೋದು ಅಥವಾ ನೈಟ್ರೇಷನ್ ಅಲ್ಲೇ ಆಗ್ಬೋದು. ಇನ್ ಆಲ್ ದಿ ಕೇಸಸ್ ಅವರ್ para product will be the major. Okay guys, so this completes our alcohols, phenols and ethers lesson, and do remember, very much important lesson, and you had to remember how to write the names, IUPAC names of these alcohols, phenols and ethers. Okay, what is the way of writing the numbers when you are having a double bond and that of your functional groups? Because there is a slight difference we have observed when you're considering your haloalkanes nomenclature and that of your alcohols nomenclature. Double bond ಮತ್ತೆ ನಿಮ್ಮ halogens ಇದ್ದಾಗ ಯಾವುದಕ್ಕೆ ನಾವು ಫಸ್ಟ್ ಪ್ರೆಫರೆನ್ಸ್ ಕೊಡ್ತೀವಿ, ಅಥವಾ ನಿಮ್ಮ ಡಬಲ್ ಬಾಂಡ್ ಮತ್ತೆ ನಿಮ್ಮ ಫಂಕ್ಷನಲ್ ಗ್ರೂಪ್ ಇದ್ದಾಗ, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಹೈಡ್ರಾಕ್ಸಿ, ಯಾವುದಕ್ಕೆ ನಾವು ಫಸ್ಟ್ ಪ್ರೆಫರೆನ್ಸ್ ಕೊಡ್ತೀವಿ ಅನ್ನೋದನ್ನ ನೀವು ಕರೆಕ್ಟ್ ಆಗಿ ಡೈಲಮಾ ಇರಬಾರ್ದು, ಕರೆಕ್ಟ್ ಆಗಿ ಅದನ್ನ ಫಸ್ಟ್ ಓದ್ಕೊಳ್ಳಿ. ಇಫ್ ದೇರ್ ಇಸ್ ಎನಿ ಡೌಟ್ ಯು ಕ್ಯಾನ್ ಜಸ್ಟ್ ಪೋಸ್ಟ್ ಮಿ ಯೋರ್ ಡೌಟ್ಸ್. ಇಸ್ ದ್ಯಾಟ್ ಕ್ಲಿಯರ್? ಸೊ ದಿಸ್ ಕಂಪ್ಲೀಟ್ಸ್ our chapter of alcohols, phenols and ethers. Okay guys, before ending this chapter, as I mentioned, let me give one example for you for your nomenclature, because we have studied about haloalkanes and haloarenes and also about the alcohols. For example, now we are having, this is of your haloalkanes. If I'm going to choose one more of your alcohols, let me take CH3, CH double bond CH, okay, then single bond CH2OH. Can you please help me with all the tetravalence is satisfied? 3 plus 1 4, 1 2 3 4, 1 2 3 4. Okay, balance. Of course, why I have given this example, remember guys, whenever you are having a double bond and that of your halogen group, okay, I repeat, whenever you are having a double bond and a halogen group, remember your halogen over here is a substituent. Okay, it is not a functional group. What it is? It is a substituent. So priority is first given to which one? To our double bond. Yes or no? So ಆ ರೀಸನ್ ಇಂದ ಇದಕ್ಕೆ ಈಗ ಕಮ್ಮಿ ನಂಬರ್ ಬರಬೇಕು. ಸೊ ಅವಾಗ ಏನ್ ನಂಬರ್ ಮಾಡ್ತೀವಿ? 1 2 3. ಅವಾಗ ಏನ್ ಹೆಸರು ಬರುತ್ತೆ ಇದ್ರದ್ದು ಅಲ್ವಾ? ಫಸ್ಟ್ ಯಾವತ್ತೇ ಆದ್ರೆ ನಾವು ಫಸ್ಟ್ ಏನ್ ಮಾಡಬೇಕು? ಸಬ್ಸ್ಟಿಟ್ಯೂಯೆಂಟ್ ನ ಹೆಸರು ಬರ್ಕೋಬೇಕು IUPAC ಅಲ್ಲಿ. ಸೊ ಅದ್ರದ್ದು ನಂಬರ್ ಉಂಟು 3, ಹಾಗಾದ್ಮೇಲೆ ಒಂದು ಹೈಫನ್, ಫಸ್ಟ್ ಲೆಟರ್ ಯಾವತ್ತೇ ಆಗಲಿ ಕ್ಯಾಪಿಟಲ್ ಲೆಟರ್, ದೆನ್ 3 ಕ್ಲೋರೋ ಪ್ರೋಪೀನ್ ಅಂತ ಆದ್ರೂ ಬರೀರಿ, ಅಥವಾ ಪ್ರೋಪ್ ಹೈಫನ್ 1 ಅಂತ ಆದ್ರೂ ಬರೀಬಹುದು. ಇಟ್ ಇಸ್ ಯೋರ್ ಚಾಯ್ಸ್. 1 ನಾವು ಬೇಕಾದ್ರೆ ನೆಗ್ಲೆಕ್ಟ್ ಮಾಡ್ರು ಪ್ರಾಬ್ಲಮ್ ಇಲ್ಲ. 1 ಬಿಟ್ಟು ಯಾವ್ದು ಬೇರೆ ನಂಬರ್ ಇದ್ರೆ ಅದನ್ನ ಮೆನ್ಷನ್ ಮಾಡಲೇಬೇಕು. ದಿಸ್ ಇಸ್ ಇನ್ ಕೇಸ್ ಓವರ್ ಹಿಯರ್. ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ದಿ? ಕ್ಲೋರಿನ್ ಮತ್ತೆ ಡಬಲ್ ಬಾಂಡ್ ಇದ್ದಾಗ ಡಬಲ್ ಬಾಂಡ್ ಗೆ ಫಸ್ಟ್ ಪ್ರೆಫರೆನ್ಸ್ ಕೊಟ್ವಿ. ಅದೇ ರಿಮೆಂಬರ್, ವೆನ್ ಯು ಆರ್ ಹ್ಯಾವಿಂಗ್ ಯೋರ್ OH and a double bond, I repeat, when you are having OH and a double bond, do remember here your OH is what? Functional group. It is not a substituent. What it is? It is a functional group. So it should get the least number. So 1 2 3 4. So numbering is starting from over this direction. So totally there are how many carbon atoms? 4 carbon atoms, no side chains. So bute ಅಲ್ವಾ, ಬ್ಯೂಟ್ ಏನಿದು ಸೆಕೆಂಡ್ ಪೊಸಿಷನ್ ಅಲ್ಲಿ ಉಂಟು, ಯಾಕಂದ್ರೆ ನಾವು ನಂಬರಿಂಗ್ ಈ ಕಡೆಯಿಂದ ಮಾಡ್ಕೊಂಡ್ ಬಂದಿವಿ. ಸೊ ಹೈಫನ್ 2 ಹೈಫನ್ ಈನ್ ಅಲ್ವಾ, ದೆನ್ ವಾಟ್? ಹೈಫನ್ 1 ಆಲ್ ಅಲ್ವಾ. ಈ ನ ಯಾಕೆ ತೆಗ್ದೆ? ಬಿಕಾಸ್ ಯರ್ ಓ ಇಸ್ ಅ ವೋವಲ್, ಆ ರೀಸನ್ ಇಂದ ಈ ನ ತೆಗ್ದೆ. ಸೊ ಬ್ಯೂಟ್ 2 in 1 all. Why I have given this example? Of course you know that there should no confusion. So whenever you are having a halogen and a double bond is given the first preference. Whenever you are having your functional group, ಯಾವುದೇ ಆಗಿರಬಹುದು, I'm not talking about only hydroxy. Whenever you are having a functional group and a double bond, your functional group should get the ಫಸ್ಟ್ ಪ್ರೆಫರೆನ್ಸ್. ಈಗ ಇಲ್ಲೇ COOH ಇದ್ರೆ ಅಫ್ಕೋರ್ಸ್ ಸಿ ಉಂಟು, ನಾವು ನಂಬರಿಂಗ್ ಮಾಡೋದು ಯಾವತ್ತೇ ಅಲ್ಲಿ ಕೂಡ ಕಾರ್ಬನಿಂಗ್ ಮಾತ್ರ. ಇಲ್ಲಿ ಹೈಡ್ರಾಕ್ಸಿ ಗ್ರೂಪ್ ಇತ್ತು, ಇದಕ್ಕೆ ನಾವು ಕಾರ್ಬನ್ ಇಲ್ಲ, ಸೊ ಅದು ನೆಕ್ಸ್ಟ್ ಕಾರ್ಬನ್ ಇಂದ ನಾನು ಸ್ಟಾರ್ಟ್ ಮಾಡಿದ್ದೀನಿ. ಎಲ್ಲಾದ್ರೂ ಇದು ಕಾರ್ಬಾಕ್ಸಿಲಿಕ್ ಗ್ರೂಪ್ ಇದ್ರೆ ಏನಾಗೋದು? ಕಾರ್ಬಾಕ್ಸಿಲಿಕ್ ಗ್ರೂಪ್ ಅಲ್ಲಿ C ಇರುತ್ತೆ, ಸೊ ಅದು ಮೇಲೆ 1 ಅಂತ ಬರೋದು. ಸೊ ವಾಟ್ ಐ ವಾಂಟ್ ಟು ಜಸ್ಟ್ ಸೇ, whenever a functional group is there and a double bond is there, your functional group should get the first preference. So if I am going to choose now one structure in this way, CH3, 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 and over here having your Br. So what you will do, ಯಾವ ತರ ಸ್ಟ್ರಕ್ಚರ್ ನ ಕೊಟ್ಟಿದ್ದಾರೆ ಅದೇ ರೀತಿ ಇಟ್ಕೊಂಡು ಏನ್ ಮಾಡ್ತೀರಾ ನೀವು, 1 2 ಅಂತ ಬರ್ಕೊಂಡು 1 ಬ್ರೋಮೋ hyphen 1,1 dimethyl ethane ಅಂತ ಬರ್ಕೊಬಿಡ್ತೀರಾ. Whether this is right? Of course not. Why? Because we know that whenever you are writing the IUPAC system, you have to select a carbon chain which will be having the largest or the longest chain ಅನ್ನು ನೀವು ಸೆಲೆಕ್ಟ್ ಮಾಡಬೇಕು, ಅಥವಾ ಮ್ಯಾಕ್ಸಿಮಮ್ ನಂಬರ್ ಆಫ್ ಕಾರ್ಬನ್ ಆಟಮ್ಸ್ ಇರಬಹುದು. ಈ ಸ್ಟ್ರಕ್ಚರ್ ನಾನು ಯಾವ ರೀತಿ ಬರ್ಕೋಬಹುದು ಅಲ್ವಾ? CH3 ಇದು ಹಾಗೆ EC ಉಂಟು. EBR ನ ಕೆಳಗೆ ಕಳಿಸ್ಕೊಂಡು ECS ನ ಮೇಲೆ ಬರ್ಕೋಬಹುದಲ್ಲ. ನಥಿಂಗ್ ಐ ಆಮ್ ಚೇಂಜಿಂಗ್. EC ಗೆ CH3 ಅಟ್ಯಾಚ್ ಆಗಿದೆ. ಇಲ್ಲಿ BR ಉಂಟು, ಇಲ್ಲಿ CH3 ಉಂಟು. ನಾವು ಇಲ್ಲಿ ಸೆಲೆಕ್ಟ್ ಮಾಡಿದಾಗ ಬರೀ 2 ಕಾರ್ಬನ್ ಆಟಮ್ಸ್. ಸೊ ಇಲ್ಲಿ ಸೆಲೆಕ್ಟ್ ಮಾಡಿದಾಗ ಹೌ ಮೆನಿ ಕಾರ್ಬನ್ ಆಟಮ್ಸ್? 3 ಕಾರ್ಬನ್ ಆಟಮ್ಸ್ ಯು ಆರ್ ಗೆಟಿಂಗ್. ಸೊ ಹೌ ವಿಲ್ ಯು ನಂಬರ್ ಇಟ್? 1 2 3. ಸೊ ವಾಟ್ ಯು ಕ್ಯಾನ್ ನಂಬರ್? 2 ಬ್ರೋಮೋ ಅಲ್ವಾ? 2 ಬ್ರೋಮೋ hyphen 2 methyl propane. Can you see the difference? So whatever the structure you have whatever the IUPAC name you have written for the structure will be totally wrong. Why I am saying this? You should analyze this structure first. Okay, whatever they have given, it is not the ultimate structure. You have to write it some other way and you have to see. But remember, whenever you are changing or whenever you are writing or change the structure, its original form should not be altered. Alva? ಈ ಸಿಗೆ BR ಇತ್ತು, ಅಲ್ಲಿ ನಾನು ಚೇಂಜ್ ಮಾಡಿದ್ರೆ ಕೂಡ ಅದೇ ಸಿಗೆ BR ಉಂಟು. ಅದನ್ನ ಯಾಕೆ ಚೇಂಜ್ ಮಾಡಿದೆ? ಬಿಕಾಸ್ ಅಕಾರ್ಡಿಂಗ್ ಟು IUPAC ನೇಮ್ ಐ ಹ್ಯಾವ್ ಟು ಸೆಲೆಕ್ಟ್ ಅ ಚೈನ್ in which it will be having the maximum number of carbon atoms. So these are the common mistakes we make whenever we are writing the IUPAC nomenclature. So avoid such mistakes. It can be only avoided when you are practicing every day. Okay, take 2 examples. You only give a structure and you try to analyze those structures. So it will be easy for you to write a nomenclature at whatever the format they may give you. You will be first, your protocol will be to analyze the structure, then write its name. Okay, so now it completes your alcohols, phenols and ethers. So best of luck.